Do-do-do. Doop-doop-doo. Ah, the stream is working. Hooray. Superb. So this stream isn't going to be about hacking or anything like that, but it is going to be about tech stuff in a way. So you might already be familiar with this beautiful masterpiece built by a guy called Ben Eater. This is an 8-bit breadboard CPU. And if you're a follower of Live Overflow, you might know he has been building his own version of this. A couple of years ago, I really wanted to build my own version of this too, except I didn't have the time or the money or the breadboard to be able to do it. But I found that just watching the videos, although they were really, really interesting, it was quite hard for me to really keep track of what was going on. And I found I wasn't really fully learning what was going on. So in order to try and remedy that, I decided I was going to try and build an emulator, or maybe it was a simulator. I'm not really sure. I'm sure some computer science people can correct me on which one it should be, of this CPU. And I've sent links to it to a couple of people now, but I think it's maybe a little bit either intimidating or hard to figure out what's really going on. So I thought I'd demo it. So it is on my GitHub, as you might have expected, and I call it Eater CPU. And the input to it is little programs like this. So if you're not familiar with Ben Eater's original version, this is one of the first programs that he wrote on it, if you can call it wrote. Really, this code is put into memory through changing dip switches, which you can see around here. So this is the memory, controls the memory address that's being written to, and then this set of dip switches down here controls the memory content. So it can be manually programmed with binary. And this particular program adds two numbers, 28 and 14. And it does that by loading the contents of memory address 14 into the A register, and then adding the contents of memory address 15 to it, calling output to add the contents of the A register into the output register, which I think is down here. It's a 7-segment display on Ben Eater's version, but it doesn't have to be. And then calls halt, which stops the execution of the program. So if I run go build, I should be able to build the code, which seems to work. Great. I'm really glad there's no errors. And if I run with a help flag, you can see I've got a single step option. So I'll run without that first. So this is the output that you get. I've used Unicode circles filled and not filled and colored red instead of LEDs. And you know, it looks like there's a lot going on here, and really there is, because computers are really complicated. But let's run it in single step mode instead and see exactly what's going on. Try and run through a program. I wrote this an ASMR voice. Thank you. Is that just a British thing, or is it a deep voice thing? I don't know. And hey, Udit Thakkar, if I'm pronouncing that right. Let's run this in single step mode. And maybe, hopefully, I can try and remember exactly what's going on. It's been a couple of years since I wrote this, and some of the terminology is a little bit, what's the word? Terse, I think, is probably the best way to describe it. So in single step mode, we can hit return to run a single CPU cycle. So here's the first cycle of the CPU. And we've got a few bits of output here. So I'm going to try my best to explain what's going on without going into too much detail. And if you really want to know more, I suggest you watch Ben Eater's videos, because they are brilliant, and he is just generally fantastic at explaining things. I think there's 44 videos on this, and they range from around 10 minutes to about half an hour long, I think some of them go up to. amazing, amazing work. Really, really is. So down the left-hand side here, I have labels for the different kinds of output, and then my facsimile of LEDs, and then a decimal decoding, or sometimes a little bit more than a decimal decoding of what the output really is. So the bus is effectively the wires that connect all of the different parts of the CPU. PC is the program counter. ADDR is the address register. RAM is the contents of the RAM in the location that the address register is pointing. The instruction register holds the current instruction, and it's worth pointing out that this is in 2 nibbles, and the most significant nibble is the instruction. In this case, it's a NOP or a no-op because it's 0, and the least significant nibble here is the argument. So we get 4 bits for each. Then we get the A register, the B register, the output register, and then the flags that are currently active. So there's some quite a few abbreviations going on here, and I'll probably have forgotten some of them because it's been a couple of years, but I'll try my best to remember what they are and explain it as best as I can. So on this first cycle, we have 2 flags set. We have CO and MI, and that's counter out and memory address register in. And that means that the counter the program counter, which is set to 0, is outputting onto the bus, which is 0, as you can see, and the memory address register is in, and also that's 0 as well. So there's not a lot going on. So the second cycle, a little bit more interesting here. So the flags that are enabled are Ramout, counter enable, and instruction register in. And hopefully you can kind of see what's going on here on the bus. So the RAM value in RAM at address 0 is 30. That's being loaded onto the bus because we are saying RAM out. And then the instruction register is reading that value in. And that's being decoded as load A14. Hi, MC Very61. This architecture is Ben Eater's 8-bit breadboard CPU. Let me post a link to the YouTube playlist in the chat, and then you can bookmark it, save it, copy it, or whatever. Mutated Nation. Cannot be streaming now. I still haven't finished your 4-hour stream. Sorry. I just got the urge and decided this would be a nice thing to do. Sorry about that. Okay, let me pull up the program .ram so we can follow it along. The text's a little bit screwy, but yeah, it's okay. So this is our load A14, and that's going to load the contents of memory address register 14, which is the number 28, into the A register, but it's going to take a couple of CPU cycles to do it. I think there's a pretty relatively common misconception that each instruction is only going to take 1 cycle to happen, and I don't know quite where that misconception comes from, but I've heard a couple of people who have that idea. So these first 2 cycles just load the instruction into the instruction register along with its argument, and that's how far we've got. And the counter enable flag, by the way, increments the counter. So note the program counter is now set to 1. And then the next cycle should be, if I can remember correctly, the start of a load A operation. So the flags we've got set are IO, which is the let me get this right, instruction register out, and memory address register in. And this is a little bit confusing here because it looks like, although the instruction register should be coming out, and there's all these 4 bits set here, there's only 3 bits set on the bus, and therefore only 3 bits set in the memory address register too. And that's because only the least significant nibble, that is, these 4 bits, are used for the argument 14. So you can see the 14 ends up on the bus and then in the memory address register. So that's the first instruction, the first cycle in the load A instruction, should I say. And the next cycle, we set the flags A register in and RAM out. So that's to load the contents of that of RAM, which is 28, into the A register here. And that's the end of the load A instruction, or at least it should be. Then we should repeat those very first 2 cycles again, pretty much. So yeah, memory address register in, counter out. So we're loading the program counter, which is set to 1, into the address register so that we can load the next instruction out of memory. And then counter enable, instruction register in, RAM out. And now we have the add 15 instruction in the instruction register. So we can start executing that instruction. And the way that instruction works is it takes the, let me get this right, instruction register out, least significant nibble, into the memory address register on the first cycle. In the second cycle, it sets B register in and RAM out. So we're loading the contents of RAM, which is number 14, into the B register. And then, so this is our add 15 instruction. The last one is Z, which is actually for sum out, and A register in. So we have effectively a really basic ALU. So when we call sum out, we get the sum of the A register and the B register. And then we, is that right? Yeah, I think so. And then we load that into the A register. So here's the answer. Then we've got another couple of cycles for the loading the next instruction, which is out with no argument, 0 argument. And then we load the contents of the A register into the output register. And we can see it's 42. Then we load the next instruction, which is halt, and then the program stops. So that might seem like a lot of work to add 28 and 14 and get 42. And you're right on some level, it is a lot of work. But at the same time, computers are doing this sort of thing all the time. I didn't think I'd worked such kind of work in a microprocessor. An 8085. Oh, cool. So my exposure to programming microprocessors is relatively limited. So the Benita YouTube series was really great for me to really start to understand how computers are working. I studied electronics at college, and I did some assembly on Z80 microprocessors and things like that, but outside of that, my exposure is limited. I've very much learned from the top down in my computing career. I started off writing, other than some QBasic and things when I was a kid, started writing some PHP in my teens, and then gradually just tried to learn more and more and got deeper and deeper. And at some point I decided I was going to start at the bottom as well and try and maybe meet in the middle one day. Maybe by the time I'm in my 50s, I'll be looking at writing operating systems and drivers and things like that. Okay, so let's take a look at the code and see how this is doing its thing. So it's written in Go. If you're not familiar with Go, don't worry too much. I don't think there's too much in the way of Go-isms in this code. So hopefully most of it should be reasonably simple. So I have a constant set for the amount of RAM that I should have, and then I represent the CPU with a struct or a structure, and it's got pretty much all of the things that you could see in the output. So some RAM, which is a map of unsigned 8-bit integers to unsigned 8-bit integers. Hi, Nemesis. Nom nom. Sorry, juice break. We have the program counter, the address register, the input register, A and B, and the bus, and the output register as well. And they're all unsigned 8-bit register numbers because, or integers should I say, because this is an 8-bit CPU, right? Nemesis, to catch you up, we're not writing a Go programming. I'm demonstrating an emulator of this 8-bit breadboard CPU that I wrote a couple of years ago. Okay, so this is all the data, and look, that I actually remember to comment them because I was writing a program about something I didn't know very much about, so heavily commented, I think. And then we have flags, which is not really a register. It's a bit field describing which flags are set. So I can see down the right-hand side here on Ben's breadboard CPU, you can see this control word. And if we look real close, I don't know if we can even see it if we go full screen. You can almost see the same abbreviations that I used for the control word as well. So that's the flags. They're saying whether we're, in this example, instruction register out, memory address register in. And then we have a couple of channels. So if you're not familiar with Go, a channel is one of Go's synchronization primitives for concurrency. So if I have two what are called Go routines, effectively two independently executing pieces of code, I can communicate between them with a channel. And I'm using them here to signal things. So my CPU emulator is going to run over a couple of Go routines, and I use two channels to signal effectively the rising edge of the clock and the falling edge of the clock too. So when a cycle starts and when the cycle's done, and there's a reason for that we'll see in a bit. As I've commented here, run should be launched as a Go routine, which effectively makes it run asynchronously. It's a method on the CPU, or rather it has a pointer receiver to the CPU, and it's an infinite loop. And what it does is it runs a cycle with these flags, counter out, memory address register in, and then another cycle with RAM out, instruction register in, counter enable. And they're the two cycles that you need to load an instruction. Then I have a map of instructions which I use to figure out which instructions need to be run for which cycles for a particular instruction. So I take the contents of the instruction register and do a bitwise AND with hexadecimal F0 to get the most significant nibble of that, which, if you recall, is the instruction part of the rather than the argument. And then for each of the cycles effectively that I get back from this instruction map, I call this c.cycle function, which we'll look at in a sec here. So here's the cycle function. It accepts an integer, which is actually a bit field, for which flags should be set. And it reads from the clock channel. So this will block until a signal is sent on that clock channel. Basically, the cycle function is kind of waiting to be told that it's okay to continue. We set the flags, and then we find these flag handlers, as it were. Range flag handlers, where does that even come from? Oh, I think that's global variable. That's a little bit cheeky of me. Yeah, that's what it is. So we get a global flag handlers slice, which we'll see in a bit. And if the particular flag has been set, then we call some function that's attached to it, and we'll see those in a bit. And then we kind of write to the cycle done channel. And we do that so that the rest of the CPU can all synchronize things. And then we have some initialization functions just to set up the RAM and that kind of thing. something to say, check if the CPU is halted, which is, say, the halt flag is set in the flag set. And then we have the bit that does the actual output, which is kind of relatively boring. I don't want to go too much into it. It's just a load of printfs, a helper function to make LEDs, and some lookups and things like that. Yeah, and they're relatively boring. It's just, if a bit's set, then output the filled Unicode character, otherwise it's the empty one. And here's our main function. So we got our single step flag, and we parse it, and we open up a RAM file, and we have a parse RAM file function that gives us the raw numbers that we need to put into memory in order to actually run our code. We create our CPU struct, add the RAM, and make our clock and cycle done channels. And then we run the CPU in a Go routine. So this bit runs asynchronously. And you can think of it as in a different thread, effectively, even though the realities may be a little bit more complicated. Go multiplexes its Go routines onto a thread pool, I believe, at least. Maybe don't quote me on that. We open up standard in a new reader just so if we're in single step mode, we can detect return being hit. And then we have an infinite loop where we say if the CPU is halted, we break out of the loop. Otherwise, we pulse the clock. So we send the an empty struct on our clock channel just as a signal, and that means that the cycle function becomes unblocked and does its thing, and then we wait for the cycle to finish before we continue. So that's the signal that comes back from the cycle function. And then we just print the state of the CPU. And if we're in single step mode, we just try and read a new line character. So that's how that works. So that's the kind of the end of main.go. But most of the interesting stuff is actually elsewhere. So let's start with the flags. Flags.go. So in here we define all of the flags as constants, and they're all commented, thankfully. I think these are in the same order that Benita uses. And we're not using all of them in our program, but you can see we've got a subtract flag we didn't use, and there's a jump as well, so you can write loops and things like that. We have a map for looking up the flag names, and then we define a type called a flag handler. And really, that's a function that accepts a pointer to a CPU struct so that it can do some modifications to the CPU in response to a flag being set. And it also has a type field, which is what we used when we were cycling through all the flag handlers and deciding which functions to run. And here they are. These are separated into output and input flags, and each one is just an anonymous function that accepts a pointer to a CPU struct, and each does something pretty simple. So all of the output ones write something to the bus. So the Ramout flag handler, for example, takes the current address register and uses that to figure out where in RAM it should be looking, and writes that to the bus. Instruction register out takes the least significant nibble, so there's a binary and there to do that, and writes that to the bus. So it's just writing the argument out. A register out just puts the A register onto the bus. Program counter out puts the program counter on the bus. Some out, though, actually needs to account for the subtract flag being set. And if it's not set, we do an addition, and if it is set, we do a subtraction. Then come the input flag handlers, and these are kind of the opposite. So these all read from the bus. So B register in takes the contents of the bus, puts it onto the B register. One more as an example. RAM in takes the contents of the bus and puts it into RAM wherever the address register is set. And the reason these are separated is they have to be run in a particular order. So the outputs have to come first, then the inputs have to come next. Because otherwise things wouldn't work properly, because they all use the bus as an intermediary, as a place to store the data in between them. So you have to write something to the bus before you can read it, which is why the outputs come first. MCVary61 says, so if there are more flags, how's it working? I'm trying to run a function for each flag. Yeah, so it runs a function for each flag. And the code we kind of looked at earlier on might make a little bit more sense now. Possibly, if I can find it. Yeah, here we go. So for each cycle, we get the flags, and we look at every single flag handler, all of them. But only if the type set in that flag handler matches, or both bits are set in the flags and in the type handler, do we actually run that flag handler. So potentially, at least, if your microcode was set up for it, which we'll look at in a minute, you could run every flag handler, and that wouldn't really make much sense because you can only really have one output and one input, and it'll be the last one that wins. So in this case, the sum out register would win, and the all of these things would be overwritten with the contents of the sum out register, so that would get a bit confusing. Hey, Lockpicking Pete, thank you. Hopefully they're continuing to be educational, you never know. And then we have some miscontrol flag handlers. So if the halt flag is set, we don't actually do anything. We have a separate check we saw earlier on to see if the CPU is halted. The counter enable flag increments the program counter, and the jump flag sets the program counter to the contents of the bus. So that means you could, for example, output the contents of the A register and read it in to the program counter with a jump flag and change where the program's executing. So that's the flags. The other really nice, interesting thing, and kind of one of the reasons that I wrote this was, in his videos, Ben has a really great few videos talking about the instruction set that this CPU should be able to support. And kind of the issue with building an 8-bit CPU on breadboard is if you want to change the instruction set, you have to actually add wires and things like that. And I thought it would be really nice if I could really easy change what's effectively the CPU microcode to change what the CPU is capable of. And I have just noticed a typo on line 18, which I'm about to fix. I'm not using the jump instruction in my add program, so it doesn't matter. Hey, Faraday. The most significant nibble is all that's used to identify an instruction. So you can see these are all 0 on the least significant nibble. And they're all unsigned 8-bit integers. So we have NOP, which is a no-op, doesn't do anything. Load A, which loads its argument, the contents of the memory address in its argument into the A register. An add, a jump, an out, and a halt. So not too many. But here's the interesting bit. Here's the instruction map. So if you remember in main.go, we used the instruction map to figure out what should happen on each cycle. That is to say, what flags should be set for each cycle and how many cycles there should be for each instruction. So for a load A instruction, we need to take the instruction register contents and put it into the memory address register, and then, that is to say, effectively change where we're looking in the memory. Then we take the contents of the memory, Ramout, and load it into the A register. A register in. They're the flags that need to be set. Don't worry about it too much, Faraday. I think if you have the time and you're interested, Ben Eater's videos, don't skip a step. He starts at the absolute basics with assembling the clock and that kind of thing, and explains every step along the way, what the registers are, and all this stuff I'm going through now in way more detail. largely because he understands it a lot better than I do. So one of the nice things about defining things this way is that I get to have a variable number of cycles per instruction. I don't have the hardware limitations that Ben does, so technically I could make incredibly complex instructions that have, maybe a dozen different cycles involved on them. But we can see, for example, the add instruction takes 3 cycles. So we need to take the instruction register contents, put it into the memory address register, then take the contents of RAM in that location, load it into the B register, and then we take the sum out and the A register in, which we saw earlier on in our program. And then we have a jump instruction, which is only 1 cycle. So take whatever's in the instruction register and set the jump flag as well, which, as we saw, takes the contents of the bus and puts it into the program counter. And out and halt is pretty self-explanatory. It just sets the halt flag. And then apparently I have a convenience function for combining an instruction and an argument. Okay, yeah, that makes sense. So I do a bitwise OR between an instruction and the least significant nibble of an argument. And there's a good reason for that, which is at some point I want to use actual numbers, but I don't want to overwrite my instruction by doing so. So that's the microcode. And nearly everything else that's left is actually just kind of relatively boring code for parsing the RAM file. So MCVery61 says, this jump different than the real world, I guess, because in the real world we don't check the condition of the 0 flag. So this is an unconditional jump. You could have a jump 0 as well. I don't have an instruction for that. I think my memory's failing me a little bit, but I think Ben Eater might have added one, a jump 0, a jump not 0 instruction to his instruction set after I wrote this. I just have the jump, so I can write loops, infinite loops, but I can't write any kind of logic. This machine's not Turing complete for what it's worth, or at least not in its current state. But it could be with a bit of modification if you want to fork the project and add your own instructions. So that's kind of everything that there is for the actual emulator itself, or again, maybe it's a simulator. I'm sure a computer scientist out there can correct me on that. And then the last bit is some shockingly hacky code to take that RAM file, add.ram, and parse it. So I initialize some RAM, which I think just fills it with 8-bit integers. Make a new scanner for the reader that's been given to this file, which is to this function, which will be the a reader for the add.ram file in our case. And then we use a bufIO scanner, a bufIO scanner to read each line of the text. If it's an empty line, we just continue. Otherwise, we call a parseRAM line function to get the address, the operation, and if there was an error or not. And if there was an error, we just return it. And if there isn't, we put the operation into RAM. So the parseRAM line function, again, I think is relatively simple. There's some error checking, that kind of thing, and then it causes a parse op function to actually figure out what the operation or what the instruction is itself. So for a NOP, we return NOP. For a load A, we have the parse operation with argument. So if you recall, that line will read something like load A14, whereas the output instruction doesn't have an argument. So it's a bit easier to just say it's out. Whereas if there's an argument, we need to let me find this. Actually find the number and then use that to create a new op using the instruction and the argument too. So that's all of the code. I was kind of tempted to try and just change this program a little bit just so we can see that it really is working and we get different outputs. So let's add 2 different numbers together. How about 9 and 10 to get 19. It's really hard to type with a microphone right in front of your face. Each CPU, .ram, yeah, 19, cool. So that's working. And what's going to happen if we add a jump? So how about in address 04, I jump to... is this going to work? Jump 1? Maybe. We want to add this with the single step mode. Not Vim, the E to CPU, please. Okay, so once we get to something being the output register, it's 19. Oh, we need to remove the halt instruction instead. Get to something in the output register, 19. And we're still at 19, so that hasn't quite worked. Okay. But it does infinite loop. So something kind of works at least a little bit. Load A14, add 15, and then output. Yeah. Oh well. I'm sure there's a reason for that not working. So MCVary61 says, can you add 128 plus 129? No, I can't. So, oh, you know what? Actually, let's just let's see what happens. That's my halt. 128 plus 129. Let's not single step it. So my answer is 1, which is kind of your classic overflow sort of a situation. So I can see I've got 129 in the B register, but I've only got 1 in the output register. And if we make this 128 plus 128, we should get 0 in the output register, which we do. Plus 127, we should get 255, which is all bits set, which we do too. So because this is an 8-bit CPU, it overflows in that sort of a situation. Cool. So that's all I was planning to stream. Hopefully you found it at least slightly interesting. I guess particularly if you've seen Benita's videos before, maybe it's interesting to see a slightly different view onto it. And if you haven't, and you're interested in how computers work, I highly recommend you check them out. Like I say, it might be a little bit intimidating looking at there being 44 videos to watch, but they really do start off with the simple bits, using a 555 timer to yeah, I should definitely download more RAM. Download using a 555 timer as the clock, and then talking about different kinds of latches, how the bus works, tri-state logic, which is something you don't tend to hear about all that often, I don't think, which it is kind of an issue where, you know, we think about digital electronics as being just ones and zeros, but really there's still analog effects going on there. So Ben's got a great explanation of why you need tri-state logic, which is basically inputs, outputs, and detached. So as for negative numbers, so technically, we could have negative numbers if we were to implement a different way to read the registers, I guess. One of the things about binary numbers is, you know, if you can just choose to interpret the number differently, right? So if you write a number in 2's complement, it has that binary can be interpreted as a negative number, or it can just be interpreted as a positive number. It's all about context. But certainly the instruction set and things that we've got here haven't been designed with negative numbers in mind. It doesn't have a way to change how it's interpreting its output, at least not in my version. Cool. So thank you all for watching. Hopefully you learned something, and more hopefully you'll go and watch all of Benita's videos, not only on his 8-bit CPU, but if you go and have a look at his playlists, if you want to learn about networking as well, or digital electronics in general, and also his series on error detection too is fantastic. So yeah, thank you for watching, everyone. Have a good evening, a good morning, or a good afternoon, wherever it is, whatever it is where you are. Bye.